you need to know that 1 mole of gas is 22.4 liters at standard temperature and pressure. Okay. That is important for trying to solve most questions that you'll encounter, or any gas question that you'll encounter on the final. Okay? So make sure you've got that nailed down. The rest of what we're talking about is kind of obligation. It's part of what we need to talk about to cover for the material, but people have found that that section is not particularly relevant for understanding or passing the overall class.
So you're saying there's no solution?
PivNert stuff? There's no PivNert stuff. What do you mean solutions? The rest of what we are talking about is gases. That is the only thing left in the section. We've talked about solutions already.
Conversions, using that conversion factor for...
This conversion factor works for what? What? STP, and more importantly, gases. It does not work for solutions because this applies to gases and only gases. If you're going to do mole to liter conversions within any other phase, i.e. solutions, that is not this expression. Okay? This expression only works for gases. What conversion allows us to convert between moles and volume in a solution? Molarity, and only molarity. Okay? You can't use this conversion for solutions, and you can't use molarity for gases. It doesn't work. Okay, so be aware of that. This is officially a new slide. It just summarizes again some of the ideal gas behaviors. We mentioned the no volume aspect, and that's why any mole of any gas will always come out at 22.4 liters, okay, because our particles have no volume. Some of the other kind of random or other useful pieces of information, all of our gas particles move in random directions. They're not attracted to one another. Okay, this means they're all kind of independent with each other. The next big thing is that when they collide, they freely bounce without losing energy, which is not something that we typically see in the real world. When you bounce two things next to each other, or you take a bouncy ball and you start bouncing it on the ground, does it achieve the same height? No, it stops eventually. Why? What's that? Why? Why does it change the height after you bounced it once? It loses some energy. How does it lose that energy? When it hits the ground, it's absorbing some of the energy into compression of the ball. When we're looking at gases, there is no loss of energy. We get a completely what's known as elastic transfer of energy right back to the ball. Dang, this is really close up here. Okay. And then your average kinetic energy of gas molecules is proportional to the temperature. Okay, this becomes relevant when we think back to PivNert. So if we look at the energy of our particles, that is directly related to temperature. As you increase the temperature, what happens to the energy of your particles? It goes up. They move more. Okay, that's your direct relationship between those. Okay. So, variables affecting gas pressure. Okay, we've already approached this subject, but let's see what we can come up with. What are some variables that affect our pressure? What was that?
Vapor pressure.
Vapor pressure is pressure. That's why they're both pressure. So, yes, the pressure does affect the pressure. Temperature. How are pressure and temperature related? As we increase the temperature, what happens to the pressure? It increases. Okay, so these are directly related to each other. So what we could go through and do is use this mathematical symbol. I already forgot what it's called. It's not an alpha, but you know, it's like an equality. Proportionality, there it is. Okay. So as we increase the temperature, the pressure goes up. Okay. And it goes up in a linear response. So we could go through and say pressure is then equal to our temperature, but with some constant, which I'll just show as a C here. Okay. That constant is going to be dependent on a bunch of other terms that we could potentially include. Okay. What else did we say pressure was related to? Pressure is related to volume. How are pressure and volume related? Okay. If we blow up a balloon, it's going to take up some volume. What happens if I now compress the volume, shrink the volume down of that balloon? What happens to the pressure of the gas inside? It increases, because as we push down, we can actually start to feel it push harder back out at us. Okay? So as we decrease the volume, our pressure increases. How can we put that into our proportionality? I can't just say pressure is proportional to volume, because then they're directly related. It's an inverse. How do we mathematically show our inverse? 1 over V. So what happens as volume, that value gets bigger? 1 over 1 versus 1 over 100. What happened to our resulting pressure? It gets smaller. So that correctly explains our relationship. We could again, and this is where ultimately our laws come in, say that pressure would then be equal to 1 over V times some weird constant C. Okay. That weird constant is going to be dependent on other things. For instance, temperature. Last thing that we could correlate our pressure to? Moles. How are pressure and moles related? Okay. Think about that same balloon again, except now we don't want to allow it to expand, so it's trapped in that size. Okay, so we blow some air in, it's going to have some pressure. And that's going to have moles. The moles are the air that we blew into it. What happens is we continue to try and blow air into it. Okay, the volume can't change. The only thing that can change would be our pressure. Does our pressure change? Yeah. What happens to the pressure? It goes up. So as we increase our moles, we increase the pressure. Go back to our expression. How would we write that? There's our proportionality. And we can again say that if we wanted to incorporate some kind of constant into this. Someone went through and looked at this and said, well, we've got a lot of constants in each of these expressions, and I can relate pressure all the way through to all of these individual things. So we said, okay, well, let's condense all of those terms down. And by condensing all of those terms, we ended up finding that pressure would be equal to our temperature times our moles over volume times some constant. Everybody see where that relationship came out? Okay. How did we discover this? Played around with plotting different experiments and looking at how pressures and volumes change, determine constants, saw those linear relationships, and put it all together into this mathematical expression. Okay. The next thing is we said constant, we picked our term to be C. Why did we pick C for a constant? Constant starts with C. Okay. Okay. We've now discovered this new constant that relates all of these terms together, so what we might go through and do is rearrange and solve for our constant. Okay. And then report our data out. Oh, I've invented this new constant or discovered a new constant. I now tell everybody this is the constant I've discovered. Okay. What's the issue with continuing to call it C?
Light.
What do you mean light?
Light is also C.
The speed of light has already been defined as a lowercase c. So while constant does begin with C, that doesn't work for us because now we'd end up using the same constant in different situations or the same symbol meaning different things. So we had to invent a new symbol. That new symbol that we picked was R. Okay, why? PivNert sounds reasonable, it's available. Let's just say that the scientists that put all this together happen to have a last name that began with R. Why not? Everybody names something after themselves. Okay. And we now have the creation of the gas constant known as R. And what was so powerful about this is that when we went through and looked at new expressions or new reactions, we rearrange, we'd end up with R equaling PV over, sorry, I have to change that order. It's starting to bother me. NT. Okay. Regardless of what situation we were looking at, we could change the pressure, which would change the volume, change the temperature, change the moles. And every single time that we went through and did this, we would end up with the exact same value. The value that technically not responsible for on the final, but if you move into 151, you would see okay. The special thing about this expression is that we now have a very advanced conversion factor. This conversion factor relates liters, atmospheres, moles, and kelvins, all in one big thing. Have we seen conversion factors that relate multiple units? How fast did you get to work today? Work, class. Miles per hour, which is an advanced unit. It relates 2 units. This is a more advanced unit because it's relating 4 different units, which means when we go through to do conversions using this conversion factor, we have to bring in 4 different units. Okay, so it makes it a little bit trickier with our conversions, but it's ultimately the same thing that you've been working with. Okay? That expression that we looked at before, 1 mole of a gas is 22.4 liters at STP. Okay. What we are specifying are our moles, which we wrote out as a unit of N. Our liters, which is a measurement of volume. T is temperature. P is pressure. That expression, or that simplified conversion factor between moles and volume, has all of the terms necessary to solve for our gas constant. Okay. It just so happens that somebody arbitrarily decided that STP, all of our reactions are run at STP, so we can go through and then solve for this expression at STP. Unfortunately, how many of our reactions are run at STP? Very, very few of them, because we very rarely run at 0 degrees Celsius. Okay? So that, again, in case you missed it the first time, super, super important expression. 1 mole of a gas is 22.4 liters. The next important expression is that we end up with our PivNert expression, which comes directly out of knowing our gas constant. Atmospheres is units of pressure. Liters is units of volume. Moles is units of moles. K is units of temperature. Okay. So if you remember your gas constant, you now have the PivNert expression. You can then go through and solve any kind of conversion factor question thrown at you. Okay. Yes, it gets a little bit more convoluted in piecing things together. And when we solve our gas law questions, we're typically breaking them into steps as opposed to doing them in a single line, okay, like we've done with our other conversions. Why? Our unit is much more complex. Our conversion factor has 4 different units combined in it, so we tend to break that down into steps. It's easier to process and think about and work with. Okay? Because of this, we can then also rearrange our expressions. We can end up with pretty much any way to go through and convert either pressure based on moles, temperature, and volume, or solve for our volume from moles, temperature, and pressure. Okay? And despite what any textbook or potentially future teachers might tell you, there isn't multiple equations. And I would argue there really isn't any equation. It's just the gas constant, and all you're doing is plugging in the proper units to get to that gas constant. Okay? So there isn't an equation to solve for, despite what it looks like. All of this is kind of generic, so let's stick with a question here. The volume of a container is doubled. Assume the temperature in moles are not changed. What happens to the pressure? Okay, there's an interesting concept. You jump straight to an idea for an answer. What happened to it? It would decrease. Why would the volume decrease? Or sorry, the pressure decrease?
The gas has more room to go in.
Okay, so we can start to just think about what happens. As the volume increases, the gas now has more space to move. Okay, if it has more space to move, what are the odds it's going to be pushing on the outside of the container? Less likely, which means less pressure. Pressure is the gas pushing on the outsides of the container. If there's more container to push on, now the particles hit the container walls less frequently, we get less pressure. Okay. The other thing we could do is go back to our general expressions that we just talked about. We said volume, was related to pressure how? Inversely. If I increase the volume, what has to happen to the pressure? It has to decrease. So that this overall result increases. Okay? Because 1 divided by a smaller number is a bigger number. Okay? So we're looking at those expressions and just trying to visualize what happens. This, more than likely, would eliminate at least 1 or 2 answers, okay, on a multiple choice test. Okay? But they are going to expect you to quantify it. So how can we go through and quantify that? Okay, well, we've got 2 conditions. We have a volume, a pressure, moles, and temperature, all at conditions 1, our first conditions. Okay. And we know that the gas constant is equal to 0.0821, this can be helpful, liters times atmospheres over moles times Kelvin, which then means pressure, I did liters, so let's do volume 1, pressure 1 over moles 1, temperature 1. What other information have they given you? Do we just have a single condition? No, we changed the condition. We've doubled the volume, which means we've moved to a new system. In that new system, I have volume 2, I would have pressure 2, I would have moles 2, and I would have temperature, 2. Do we know anything about those new systems, or that new system? What do we know? We know that the volume was doubled. That means volume number 2 is what? Twice our starting volume. So 2 times volume 1. Temperature in the moles didn't change. So T2 is not really T2, it's N2 is not really N2, but N1. What is P2? Okay, we don't know it yet. Well, that's what they're asking you to solve for. What happens to the pressure? So we could put that in as an X. Where does this help us out? Well, if I relate the volume, the pressure, the moles, and the temperature at our second condition, those are all going to be arranged into the gas constant, which will equal 0.0821 liters, atmospheres, moles, Kelvin. Right? So if I take V2, P2, that must equal the gas constant. Everybody okay with that? Okay, I don't like your expression, so I don't believe you. Try that again. What do you not like about that? Okay. The gas constant is always a constant. So all we have to do is take our terms and slide them in. You'll notice that we weren't given any real numbers to solve through here except a 2. What you are trying to do is convert all of that text into some equation format. And that's why we've been slowly stepping through it. Okay. Under our second conditions, we could go through, and instead of saying it's R, it's R2. The gas constant for conditions 2 will still equal volume times pressure over moles times temperature at those conditions. What is special about R2 and D2? No. And R1? They're a constant. They are the same, which means I can set these expressions equal to each other. If we tried to solve this expression as written, we would have a hard time. But we also have this information. So let's make those substitutions. What did we say V2 was? 2 times V1. What did we say P2 was? X. What is N2? What is T2? I know these two expressions equal each other. Solve for our unknown, which is X. So get X all by itself. What do you need to do? What's that? Sorry, I still couldn't quite hear you. Say that again? I got you. Sorry. So what you've suggested is that we need to now move, so now I'm going to clean up some space here. I need to move 2v1 away from the x over there. How do I do that? Multiply by what? 1 over 2v1. Why? It needs to cancel the unit. Okay. So what happens to 2v1 on the left side? It would cancel, which is exactly what I need it to do. The new expression I've got, we erase all of those, would now be x over n1 times t1 equals that other expression. How do I get the n1 and t1 over to the other side? Now I can multiply. If I multiply by n1, what happens to my n1s? They would cancel. How do I get the t1 over the other side? Same deal, multiply by t1. Let's cancel, what do we end up with? Simplify the left-hand side of the equation. What happens to the t1s? They cancel. What happens to the n1s? What happens to the v1s? And what do we end up with as an expression? 1 over 2 P1 equals X. What did I say X was? Pressure at our second condition. What happened to pressure at our second condition? It is exactly 1/2 of our initial pressure. So it decreased by 2-fold. There's our quantifiable answer. No numbers given, and yet we can still go through and solve. You have to go through and use your algebra skills and all of those different fun little things that you learn in your algebra classes. Okay? And everybody loves that. Did I just hear what algebra skills? Okay. So let's switch it up to an easier question that we actually have some numbers on. How many moles of neon gas occupy 2.34 liters at STP? Two approaches to solving. Okay. And I know this is where people can get mad at me, that's fine. Okay. We're going to go through and show the correct way, in my opinion, the one in red, the one that applies to all circumstances, and then we'll go through and show it in purple, which is the way that applies only at STP. Okay, since we're at STP, we can get away with the short method, but I want to again emphasize the fact that that only works at STP. If we change the temperature and pressure, your whole system goes out the door, and using that conversion would mess you up. So we would write down our ideal gas constant, 0.0821 liters times atmospheres per mole Kelvin, which then tells me I need volume pressure over NT equals my gas constant R. I would write down all the values I'm given. I'm given volume. I'm told that I need to solve for moles. Am I given pressure and temperature? How am I given that? It says STP. So you have to convert the term STP into those numerical values. Once you have that, or at least the way I would do it, is I would then go back up to my expression, and I would rearrange that where I can then solve for N. N, whoops, will then equal volume times pressure over T times R. Did I do that right? Yeah. No, because you can multiply N by both sides. What did I say the volume was? Pressure, temperature, my R, 0.0821 liters times atmospheres per mole times Kelvin. My liters will cancel, my ATMs will cancel, my Kelvins will cancel. Okay. Anybody have any issues canceling the units as I just drew out? Okay, I'll kind of take that as a no. I do think it is a bit confusing personally because you have units, division within a division, and that can be confusing. We'll address that in a little bit here. We can now punch into our calculator and we'll get some number, and our unit would be 1 over moles. That's just straight out of what the equation tells you, is 1 over moles. Does everybody see that that's what it says? Okay. Okay. Let's convert that into something that we can numerically work with a little bit better. What is 1 over 2? 1 divided by a half is 2. Mathematically, that comes out to be moles in your numerator. Okay. We don't have to do anything with our number. All we got to do is punch that into the calculator. 2.34 times 1 divided by 273 divided by 0.0821, and we have our answer. This format works for all gas expressions. Did anybody go through and solve it that way? Yeah, I kind of suspected you didn't. That's okay. Because we are at STP, we also know that the liters and moles of neon are directly related. We have a conversion factor for that. What is that conversion factor? 1 mole is 22.4 liters. In a single step conversion, we'd end up with our answer. Okay. Yes, the bottom one is quicker and faster, but it only works at STP. Okay. For better or worse, we tend to ask questions at STP, so it's almost always easier to go through and do this conversion. Okay. Again, I don't like it because it doesn't apply out into the larger world. Okay. Either way you solve it, what are you going to end up with? The exact same answer. It's beautiful in that respect. Yes?
So for the first part, when you do the 1 over 1 half and it equal to, where does the 2 go?
So that 1 over 1 half was only used as an example because the 1 over 1 half is roughly the same as 1 over a mole. So we use the 1 over a half to say that that was equal to 2 to help us see that 1 over a mole is just a mole. All we're doing is swapping whatever that bottom denominator is up to the numerator. Yeah, so the half was only there as an example to see what happens with the unit. That number has nothing to do with your calculation.
So that what algebra skills wasn't so much of a joke. How'd you get the n equals volume over pressure? Because I tried to do it that way, but I got it very different.
So to convert that, is everybody okay with what's written up there? We're going to go through and show a little bit of algebra here. Okay, and I just need some space. What do we see? R VP over NT. Okay, so there's a couple ways we could approach this. We could try and take all of these terms and send them over to the left side. Okay. To do that, I'd have to divide by volume, divide by pressure, and multiply by temperature. Are you okay with that?
Yeah.
Okay. If I went through and did that, then to get to the other side, I'd have to divide by volume, divide by pressure, multiply by temperature. Yeah?
Yeah.
So I'd end up with T times R over PV equaling, no, 1 over N. Is that the answer you wanted? Are we solving for 1 over N? What are we solving for? N. Okay. Yeah, I don't want to go that way, but yeah, you can do that. So the other approach was to get the n over to the other side because it's currently in the denominator. So what I want to do is get it into the numerator. To do that, I'll need to multiply both sides by n. But then I would end up with nr equals Vp over T. Well, that's nr. I didn't want nr. I wanted. So how do I get the r to the other side? Now I can divide by r on both sides. And I would end up with n equaling Vp TR. Okay. I just want to address what you said there in the back. I think that was you, Jacob. I already forgot our expression. Was it TR over VP? Okay. So what he said was just take the inverse of everything. If you go through and do your calculation and you followed your units correctly, if you went through and solved this, your unit at the end would come out to be 1 over moles. Well, that's crap. I didn't want 1 over moles. I wanted the moles the other direction. Okay, so let's say we solve this out and we got 0.2 moles, or 0.2 1 over moles. Well, if I wanted to solve for moles, what I've solved for is the inverse. Well, that's technically wrong. Instead of going back and resolving everything, what can I do? Take the inverse of the result I've already got. Okay. So if I now take the inverse of this whole thing to the minus 1, which is the same thing as saying 1 over 0.2 1 over moles, I would end up with 1 over 0.2 moles. Okay. If you don't like that, that's fine. Ignore it. I didn't tell you that. But it works. Okay. The other option is going all the way back and resolving everything. Okay. Questions? Okay. Dalton's law of partial pressures. I've heard that a faculty member calls this the duh law. I don't know if I would go really that far, but it's after we discuss it, it might make a little more sense. If we take a closed container, okay, according to our ideal gas law, none of our particles interact with each other. Okay, so they are all individually contributing to the pressure. If I want to look at the total pressure within the system, what do I need to look at? What about the whole system? A summation of each of the particles that are contributing to pressure. So the pressure of every particle pushing against the wall. So my total pressure is going to be equal to the pressure of my parts. Those parts can be all the same atom, or the same type of element, or they can be different elements. Typically, they're different elements, because what we're looking at is saying, well, I can determine the pressure for all of the CO2 gas particles. I can determine the pressure for all of the oxygen gas particles. What's my total pressure of the system? So if I just have a closed box and I've got CO2 in here and O2 in here, each of those particles is going to be contributing a pressure. Since I was likely the one that put the CO2 in there, I know the pressure of the CO2. Since I was likely the one that put the oxygen in there, I know the pressure of the oxygen. What's the total pressure going to be? It's the pressure of both of those particles combined. This is the law of, or Dalton's law of partial pressure. When is this valid? When you're looking at gases, number one, and potentially more importantly, depending on the level of instruction, ideal gases. As soon as your gases stop becoming ideal, this expression starts to fall apart. Okay? But by that same token, so does the ideal gas law. Okay? So when you're looking at the Dalton's law of partial pressures, all we're saying is the pressure of each particle or each gas summed together will equal our overall pressure. That's it. Okay? Where these can become a bit obnoxious is that we might go through and tell you how many moles of CO2 we have, and we might tell you how many moles of O2 you have, and say, oh, we're at standard, well, we can't quite do that, and we're at a volume of 2 liters. What is the total pressure for the system? Well, you'd have to calculate the pressure for CO2 and the pressure for O2, and then you would add those two values with each other. Okay? So you may have to break it down into separate equations or separate solves. You'll end up having to solve for the pressure for each of the independent ones first and then add it all together. Okay? So a sample of noble gases contains helium, neon, argon, and krypton. Partial pressure of helium is 125 millimeters mercury, neon's 45 millimeters mercury, argon's 158. It's a lot of numbers. Continue. What is the total pressure of the sample? Well, how would you solve it? Pressure total just equals the sum of all of those gases. Okay, and I don't feel like writing all those numbers. So we just write all those numbers down, add it up, and we get our answer. How could we make it more obnoxious? Because that's what we're all about, right? Now what's the problem? The units aren't all the same. You can't just add them up. You have to address your units first. Okay? Or we could even go through and say, whoops, moles. Even more obnoxious, we now have to convert our moles into pressure and sum everything up. Make sense? Okay. I think it's 2 slides, I promise. 4 slides, 3 slides, something like that. Absolute zero. One of the things that comes out of looking at ideal gases and the ideal gas expression is this idea of absolute zero. Okay. If we go through and solve PV equals nRT, our pressure. Give me a value for any pressure. 5. How about another value? 7. Another value. 10, 16. What do all those values have in common? Okay. They're not 0. That works. They're all whole numbers, yeah, but we could do 0.5. They're all positive values. How about our volumes? What are our possible volumes? All positive. Possible moles? All positive. Gas constant? Always the same and always positive. Which means what happens with our temperature? It's always positive. And we don't even have to worry about Kelvin necessarily in this way we are looking at it. If our pressures are positive, our volume is positive, and our moles are positive, and the gas constant is positive, the temperature by definition has to be positive, which is one of the reasons why degrees Celsius doesn't work within this expression, because degrees Celsius gets you a negative value. Okay? So we have to be running in a new temperature unit, or an absolute temperature scale. And when we're referencing that absolute temperature scale, we cannot be negative. So theoretically, we could go through and extrapolate this information out to find out that the absolute lowest temperature we could possibly get would be 0. That is our absolute value. That is our absolute 0. Okay. Leave it to a physicist. I think it was a physicist. Okay. Vaguely remember mentioning this earlier in the semester. They have reported negative kelvins. Okay. Not 0, but negative kelvins. That's a complete mind mess, if you will. Okay. Comes out of mathematics and theoretics and all sorts of other weird stuff, but they've been able to do it. Okay. How is a good question. Okay. But guess what happens to the ideal gas law when they did it? Exactly right. That's a nice sound effect for it. The ideal gas law becomes null and void because we can't have a negative temperature. Okay. So all we're trying to say is that if we move to a situation where we've shrunk the volume down infinitely small, the pressure down infinitely small, okay, and our moles down infinitely small, the lowest temperature we could ever achieve should be 0. That is our absolute system. And that's where Kelvin ultimately came from, was looking and modeling our ideal gas systems, looking at the relationships between those terms and realizing, hey, the degrees Celsius system doesn't work for us. The Fahrenheit system doesn't work for us. We need a more scientific value. Yeah?
Well, when they achieve negative temperatures, don't they kind of get past 0? Doesn't the system jump to past 0?
Yes and no. You get into all sorts of quantum physics stuff, which I can talk to you after class about. We don't need to make it even worse than it needs to be. Okay? So absolute 0. Temperature 0 Kelvin is the lowest we can go. Which means what's the lowest degree Celsius? Negative 273 degrees Celsius. Absolute lowest we can go. Okay? Kinetic theory of gases. Oh, this is fun. This is officially the second to last slide. Why do gases fill the entire volume that contains them? They spread out. Okay? There is nothing keeping those particles next to each other. They are constantly moving out away from each other, which means they are going to fill whatever space is trapping them in. Okay? There is no attractive force between the individual particles. What happens to the amount of motion of a gas when we change the temperature? Increases or decreases respectively, which means as we increase temperature, what happens to the motion? It speeds up. Okay? As we decrease temperature, what happens to the motion? It slows down. So we're just seeing that direct relationship between those. If, heaven forbid, you have to move into 152, okay, someone is going to mention a term about entropy. What is entropy?
It's like death.
Everybody's told the measure of disorder within a system. Okay? I would change that around. It's not the measure of disorder, it is the measure of motion. The more motion you have, necessarily, the more disorder you're going to get in it. If you go through and think of entropy as a motion as opposed to a disorder, it's a little bit easier to grasp some of the conceptual issues when it comes to entropy. Which moves faster, hydrogen or krypton? Why would hydrogen move faster than krypton? It's a lighter gas. If we give them the same amount of overall energy, okay, a lighter molecule can then translate that energy into moving more than the larger gas. The kinetic energy of a sample of krypton gas compared to hydrogen gas at room temperature. Same temperature. Let's not even evaluate that. Ready with the last slide?
So yes.
You're welcome. We're done. 10, 25 minutes. All right. I am more than willing to go through and answer any questions you may have about any of the concepts covered throughout the entire semester. If you have absolutely no questions, then good luck on the final. I'll see you next Thursday, bright and early at 7 a.m. If you have absolutely, or if you have questions, might be a good idea to stick around and get those questions answered. So I'll give you the next, let's say, 5 minutes if someone wants to take off, to go ahead and take off, pack up, and do your thing. So if you can get out in 5 minutes, everybody else that has questions can stick around and we'll get questions answered. We'll go ahead and write that information. No.
Mike.